Hello and welcome to this video. In this video we are going to look at the topic of transformers. So this is now another use of magnetic fields, another use of electromagnetic induction, where we're going to have to look not only at how these things work. So you would have heard of transformers before at GCSE for most people, but now we're going to go into more detail. We're going to build on the knowledge that you have. We're going to go into how they work, and also we're going to add on maybe some issues that we encounter and some solutions that we can have. So let's first revise some of this GCSE knowledge as to what exactly are transformers. So transformers are devices that are placed in the national grid. Okay, now the national grid is a kind of system of transferring electricity around the country, right? So we start off at a power station. So we have some sort of power station where we have this electromagnetic induction taking place in order to produce these AC currents. Then out of the power station, it goes straight into a step-up transformer. Okay, so this is one of the two types of transformer. The purpose of a step-up transformer is to increase the voltage or increase the potential that is traveling through these wires, because from then we then transport it across countries through these pylons that you see when you go on the motorway and stuff. And then you have a step down transformer, which has the purpose of decreasing the voltage. And as soon as you've now decreased the voltage, then it will go into people's houses and household appliances and such. So the first thing we have to do is try and explain how these things work. Okay, so we know we need the step up and step down transformers to try and increase the voltage and decrease the voltage, or increase the potential or decrease the potential. How exactly do we do that? So we first have to look at what exactly is a transformer. So a kind of setup of a transformer is we have a metal core. Okay, so we have some metal core like this. So this is just kind of a core, and then from the power station, we have a coil of wire that wraps around this core. So let's say this is my primary coil, okay? And then I'm also going to have a secondary coil. Now I'm going to take the case that this is a step-up transformer, and we'll explain the difference between step-up and step-down in a second. But that means that my secondary coil is going to have more turns on the coil. Okay, so this means if NP is the number of turns on the primary coil, in the case of a step-up transformer, that is less than the number of turns on the secondary coil. Now, in order to give this idea of what's happening here, this is a metal core. Okay, so the actual purpose of this is that in actuality, when we do this, we won't have these two coils. We won't have the primary and secondary coil being so far apart. In actual fact, we'll probably have the same coil, and we'll just interweave. So the primary coil will maybe do something like this, and the secondary coil will go in between these loops, okay, and wrap around the same column or coil. Now, the reason we don't use diagrams like this when we're explaining it is because this looks like a mess, right? This isn't very helpful. So what we're doing in this diagram, and this is how most diagrams are set up, we're purposely separating them so that we can see what's happening in each of them. But in actuality, we want to make these cores as close as possible, or these coils as close as possible. So how does this increase the potential that's traveling? So what we know is that there is some current, some AC current that is traveling in the primary coil. So there is an alternating current in the primary coil. Now, having an alternating current in the primary coil means that I have movement of electrons. Now, if I have movement of electrons in this coil, it means that coil is producing its own magnetic field, okay? Because we know that we can have a force producing a magnetic field. So if we've got the electromotive force, which is what's causing these electrons to move, that's going to cause a magnetic field. Okay, so this primary coil then acts as a bar magnet, okay, where we have kind of these magnetic field lines that are going to trace outwards. Now, because this secondary coil is going to be as close as possible, this secondary coil is actually going to cross these field lines. And we're going to, since we're drawing it in this case, they will cross those field lines. Now, these are two separate wires, which means that actually, if we want to take the electrical energy that we have in the first wire and we want to convert it to the second wire, we have to have some sort of induction here. So we have to induce an EMF. Now, we need to turn back to Faraday's law and say that the only way we can induce an EMF is by having a change in the flux over time, okay? Remember, the change in the flux means I can either change the magnetic field strength or I can change the cross-sectional area that is parallel to the flux. Now, in order to change the area, I would have to physically change the dimensions of the secondary coil. Now, that's going to be extremely difficult. We need some sort of system that's going to constantly like tighten it and then loosen it, and that's just going to be too much. But because we have an alternating current in this primary coil, the magnitude of the magnetic field is going to vary, okay? Because this magnetic field is going to keep changing directions. Remember that when a solenoid like this, when we have with this coil of wire, has a current traveling through it, it will form a north and south pole. Now, we know that the direction of the field lines always go from north to south. So if we're then going to change the direction of the current, we're changing the direction of the north and south poles, which means we're changing the direction of the field lines. Therefore, we're going to have this kind of pulsing effect where we're going to increase the magnetic flux density, then it's going to decrease. So we are actually going to be changing the magnetic flux density, and hence the flux, across the secondary coil. And this then induces an EMF in the secondary coil. So the changing magnetic flux density induces an EMF in secondary coil. Now, we know that this EMF that we're inducing in the secondary coil has to be larger than the potential or the EMF that was in the primary coil, because our whole purpose of this is to step up the potential, which means this then explains why we have this condition here for a step-up transformer. Okay, so this is a step up, because from Faraday's law here, we can say that the EMF is going to be proportional to the number of turns on that coil. And since I now have an increase in the number of turns, and I know these are proportional, that must mean that I also have an increase in the EMF, okay? And this is the whole idea of a step-up transformer. We just have this kind of alternating current that then causes a changing magnetic flux density, which then leads to an induced EMF in the secondary coil that will be larger due to a larger number of turns on that secondary coil. Now, the same can be done, or the same can be said for step-down transformers, except in a step-down transformer, we would want the secondary coil to have less turns than the primary coil. Okay, so for us to step down, the number of turns on the primary coil should be greater than the number of turns on the secondary for a step down, because that means then that if they're directly proportional, a decrease in the number of turns means we have a decrease in the EMF. Okay, since the the magnetic flux density going through both of these is going to be the same. Okay, so that then means if we have the EMF being transferred, we know from way back in GCSE, or even what we've done in AS, that this EMF, this potential difference, is a measure of energy. Okay, so somehow to get from the primary coil to the secondary coil, it appears as though we've increased the amount of energy. Okay, but then we have to go back to our strict definition, which is that the EMF is actually the work done per unit charge. Okay, so now if I've increased the EMF, it means that I've given each of these charges more energy, right? So each individual electron now holds more energy. However, in order to conserve power, so the total amount of energy that's being transferred, I have to make sure that I have less charge being transferred per second, right? So in order to conserve energy, I have to have each electron gains more energy. However, there's multiple options that I can have. I can either have the case where I have less electrons flowing. This is quite a difficult case to manifest, because you've got basically a very, very long wire. So surely you're going to have more electrons there. The second case then is that these electrons don't flow as quickly. They have less kinetic energy because it's all stored as electrical energy. Okay, so that means that we have less current because we've got slower movement of electrons. Now, if we have a slower movement of these electrons, we have less current. It means we've conserved power, but having less current then leads to less resistance, right? So if I have less, if these electrons are moving through this metal lattice slower, that is then going to lead to them having less frequent collisions and therefore wasting less energy. So less current means less resistance, and less resistance means less wasted energy. And this is the whole purpose of these transformers. The step-up transformer has to increase the voltage and decrease the current so that we can have like miles long wires that can conduct that electricity without losing it all along the way, because we know it's fairly if we've just had a wire with a very, very long distance, the resistance of that wire is going to increase massively. Okay, and you can look back at the resistivity equation and look at the proportionalities between the resistance and the length of the wire. As the length increases, the resistance increases. So what we would be expecting is that we would just waste all of the energy in the transmission from one position to the other. The reason step-up transformers are so good is because they then allow us to conserve that amount of energy and maintain these being the most efficient that they possibly could be. The step-down transformer will do the same thing, except now you're trying to decrease the potential, and the purpose of a step-down transformer is less to conserve energy and more to just prevent your household appliances from blowing up. Okay, each of your household appliances has a certain power rating, has a certain amount of current or potential that it can hold, and these step-up transformers can take it up to potentials of a few kilovolts or maybe more. If you were to put maybe a kilovolt across your phone battery while you're trying to charge your phone, you're going to end up with your phone exploding. Okay, so the step-down transformer is for safety, in order to ensure that all of the devices in your house don't overload. So devices don't overload. Okay, So this is our general idea of how these transformers work. And a key thing is that, so referring back to this, the key thing is it has to work with alternating current, right? Because that's what causes the change in magnetic flux density. If it was a direct current, there'd be no change, and therefore we'd have no EMF induced. Now, I mentioned briefly this idea of efficiency, and I said that increasing this EMF makes this more efficient. Why I should specify that it makes it more efficient for transmission in the wire, because I'm losing less energy. But I can also say that I have an efficiency in how much energy I'm transferring from the primary coil to the secondary coil. So we can then quantify that by the variables that we are aware of. The efficiency of a transformer we can calculate, because we know that efficiency as a definition is just the useful power output, or the useful output, divided by the total input. Yeah, so we're saying it's the how much useful energy we're actually getting out, and how much of that energy did we put in. Okay, now in this case, the useful output is the power in the secondary coil. Okay, now we also know that we can calculate power by saying power is equal to the potential multiplied by the current. Okay, so I can say that my efficiency of this is going to be the useful output, which is the potential across the secondary coil, multiplied by the current across the secondary coil, divided by the total power input, which was the amount of electrical energy that we had on the primary coil. So this was Vp IP. And this is on your formula sheet as a calculation for the efficiency. Okay, so this is the first of the two equations that you get for transformers. The second of which is explaining the relationship between the two coils. How can we assess how much of an increase an extra turn on the secondary coil would be, for example? How do we predict what we should be seeing as a maximum, and then we could use that as a percentage to calculate the efficiency? And what we find is that what we can relate pretty easily from something we've just said is that the EMF, and in the case of what we're going to say, we're going to refer to it as the potential, is proportional to the number of turns. Okay, which means that their ratios of potentials should be equal to the ratios of the number of turns. Because I can say that this is true, and I could even do this probably more mathematically and say that Vs is the same as Kns, where Vs is the potential on the secondary coil and Ns is the number of turns on the secondary coil. I could also say that from this, Vp must be equal to K times Np, right? And I can say K is the same for both of these, because it doesn't really matter if I'm talking about the difference between them. I can say I know the constant of proportionality is going to be the same, because that's just the change. So this basically means that K is the change in flux over the change in time, which is the same for both of them. So if I rearrange these, I can say that Vs over Ns is the same as K, and Vp over Np is also the same as K. And that then leads me to this idea that Vs over Vp is equal to Ns over Np, and hence the ratios of these two are the same. Now, this equation is useful when you're trying to predict what the potential across the secondary coil would be, or what the potential across the primary coil would be, or how many turns would you need to produce this potential, and so forth. Okay? And these are the only two equations that you actually get given for transformers. You will be asked, obviously, to apply Faraday's law to transformers as well. Now, the last part of transformers that you have to be aware of are the issues that we come across when we try and utilize transformers in the real world. Of course, we have these calculations that mean that we can calculate efficiency and we can look at the relationship between the voltage and the number of turns, but when we actually come to perform these processes, the efficiency is basically never going to be 100%. Okay, so then we need to look at what issues lie in the way of the efficiency becoming 100%. So we're first going to redraw out this kind of rough diagram of the transformer. So let's have the core here. So this is the core with the primary coil and the secondary coil, and again this is a step up because there are more turns, so NP is less than NS, therefore it is a step up transformer. Now the issues that we're going to talk about aren't just for the step up transformer. This is just the example diagram that I'm going with. This will happen for both step up and step down transformers, and our issues begin in quite a simple way, I guess. So as soon as I induce an EMF in the secondary coil, I will get a current flowing through that secondary coil. If I therefore have a current flowing and this wire has some resistance, that then means that I'm losing energy instantaneously. Okay, so the first issue is quite an obvious one, which is just I have resistance in these wires. Okay, and I don't want resistance in the wires. Okay, and that leads to wasted energy. Okay, now the rest of the issues aren't as straightforward as this because they involve this metal core. Okay, so this metal core, we actually can now specify that this is usually an iron core. Okay, now the second issue that we have is something called an eddy current. Now eddy currents are also going to be a manifestation of an electromagnetic induction where we don't want to have an electromagnetic induction. We are trying to make sure that we have electromagnetic induction occurring in this secondary coil. However, these flux lines are crossing this metal, which is a conductor, and hence what we find is that along these barriers here we end up with eddy currents. Now what an eddy current is where we have a current induced that is just going to travel around in loops on this iron core. So we have a current induced in the iron core. Okay, now if there's a current induced, that must have been due to an EMF that has been induced there. And if we're now inducing EMFs in the metal core, that then leads to us losing energy because that energy that we've used to induce that EMF could have been used to go onto the secondary coil. This again leads to a waste in energy. And this is another problem. The third problem is something called hysteresis. Now, hysteresis might not have been a word that you guys would have come across. I feel like a few teachers will probably have introduced this to you, but it's not a necessary word for you to know for A-level. But the idea of hysteresis is that if I'm now going to have a current induced in this wire, that means that I now have another current which is going to produce another magnetic field, because like we said with the solenoid, if I have a current flowing, it produces its own magnetic field. This means I am taking this iron core and I'm magnetizing it. So I'm turning it into a magnet having its own magnetic field, and then when the current decreases through the primary coil, I'm then demagnetizing it because I'm taking away that current. I'm no longer inducing that EMF, so it will then magnetize and demagnetize. Okay, now hysteresis is the fact that if I were to plot out the magnetization of iron, I would end up with this kind of graph. So I'd start off by increasing up to here, then I'll find that I will decrease down to here, and then I will come back to here. And you can search for hysteresis curves on Google to see other examples, but generally this is the idea. I'm magnetizing it and demagnetizing it, and that requires energy. What we find is the amount of energy that we lose is equal to the space in between these two lines. Okay, so it's a loss of energy from magnetization and demagnetization. And now we have a question of how do we reduce these wasted energies, because these are 3 examples of ways that we can waste energy in these transformers, but obviously we're trying to avoid this, and we have some solutions to each of these problems. Now, the first solution is we're looking for something to have a low resistance, so we just need to decrease the resistance of the wires. Now, in order to do that, you can either find wires that just naturally have a lower resistivity, or you can just use thicker wires, right? So you can use wires with low resistance, okay, or you can use wider wires. Now, the reason wider wires then decreases the resistance is because if you have a larger surface area for the electrons to travel through, you'll end up with less likelihood of collisions in this metal lattice. In order to solve this idea of eddy currents, we are trying to prevent currents from flowing around this metal core. Now, in order to prevent currents, we need to insulate it. So we're trying to do our best to prevent currents from flowing. So what we do is we laminate the core. Okay, now laminating the core means that we are just going to try and cover it in plastic, and we're trying to put plastic in between small segments so that we prevent current flowing, because obviously current can't flow through plastic. So if we then put as much plastic around this core as possible, we're preventing that current from flowing in the first place, and therefore we're not going to have this wasted energy from these induced currents. The third problem that we have is the hysteresis, and the way we solve this is it requires energy to force this iron to become a magnet, and it requires energy to demagnetize it. So what if we find a material that will just more easily magnetize and demagnetize so that we don't have to put in as much energy? It's kind of impossible to completely prevent us from having magnetization and demagnetization of the iron core, but it is possible to reduce the amount of energy needed to magnetize and demagnetize it. And so what we do is we, instead of having an iron core, we have a special alloy that just makes this a little bit softer. So soft iron core, because this is easily magnetized and demagnetized. Okay, and this wraps up then everything that you need to know about transformers. You need to be familiar with their uses, you need to be familiar with how they work, you need to be familiar with the equations for efficiency, and also the equations for the relationship between the potential and the number of turns. You need to know their issues and how you solve all of those issues. Thank you for watching.